what I'll cover today is neural-symbolic artificial intelligence, state of the art, what's missing, and what I think are the next steps. So what is this neural-symbolic field? So it's really the merging of symbolic AI and neural approaches. This has been an old debate, which approach is better. Is it symbolic? And I'll describe what each of these are in a second, but you've maybe heard of this sort of debate between one approach versus the other being categorized in many different ways. So logic computationalism is sort of the symbolic representation. Connectionism is a name for neural approaches. Also been categorized as symbolic versus subsymbolic. An older term is neat versus scruffy. Neat being the neuron based work, where scruffy is the symbolic. And so this kind of debate has been going on for many years, ever since the 80s. And so there's been a lot of different iterations. Minsky has this nice kind of diagram in one of his talks about this, where what we're really talking about here are these two sort of paradigms. One is sort of very structured, the other one is very dynamic. And, arguing about which one is better is maybe not the best way to move forward. Maybe what we should focus on is work together and come up with solutions that are able to take advantage of both approaches. So what exactly are these two different approaches, symbolic versus subsymbolic? Symbolic methods are ones that use logic. They use symbols to represent entities in the world and relationships between them. And so a lot of these are represented as logic axioms. There are explicit symbolic programming methods and rules that people create. You're able to perform inference, reasoning, and different types of search. You can model AI systems to perform decision making. Many people have defined different types of programming languages to be able to do this. These languages reason about a different set of rules, ontologies. They're able to generate plans towards some goals. Systems that have been implemented specifically for the rule-based systems are expert systems. They have been used to create theorem provers. And what is currently a very hard topic in the symbolic and actually in the subsymbolic domain, as I'll show you in a second, common sense reasoning. Common sense reasoning is actually a very difficult topic. It requires a lot of intuitive information that people sort of learn as they grow, but it's really hard to actually implement in a system, such as a symbolic AI model. What is subsymbolic? So this is connectionism. It's systems that learn from data. Right? So you've probably heard of Bayesian learning, deep learning. Another term might be soft computing, statistical learning. So these are neural networks. They use backpropagation, reinforcement learning, and any number of acronyms that you can think of. And these kinds of tools are good at classifications and making predictions. Now, what about these other systems? Where would they fit in? Are they symbolic or subsymbolic? So fuzzy logic sort of sits in the middle between these two. Agent-based simulation, it requires kind of a lot of different components, a lot of different moving parts, but it also requires different concepts, different states explicitly defined, different set of rules to dictate how different agents interact together. So it's not quite clear where these kinds of systems fall in. Are they symbolic or subsymbolic? And what I will try to sort of show you is that they're actually both. We've been working with hybrid systems for a very long time. We just haven't maybe named them as such. So what is so great about symbolic? What do they actually provide, symbolic AI? So introspection is more useful for coding. These kinds of models are easy to debug. They're easy to explain. So explainability being a big important topic right now. So symbolic models have always been explainable just by their very nature. They're easier to control. You don't require as much data as you might with sub-symbolic models. A lot of the data that's actually put into these symbolic models is taken from experts. So subject matter experts will come in and provide information that they have sort of gathered over their career. And those that knowledge is then implemented as a set of concepts and relationships between those concepts that you can then reason with and infer new information. Because of all this, symbolic AI is more useful for explaining people's thoughts. So you can actually try to follow a person's thinking pattern to understand how they make decisions at their work or in their life or in whatever context. And symbolic AI is better for abstract problems. What this means is if you take an abstract idea that may be not sufficiently defined, that you can actually start collecting data about it. But intuitively, people sort of understand these concepts like happiness or sadness. It's really hard to sort of understand what these things are or how to identify them truly, right? So it's not just a matter of person smiling, right? You have to sort of understand their context, what they're smiling about. And so these sort of abstract ideas are much more easily represented as individual concepts with sort of semantic relationships between them. Now, I'm sure many of you have seen knowledge graphs. So this is one example of implementing these kinds of ideas on a large scale in a database. Now, what about sub-symbolic models? They're much more robust against noise. They generally, at least nowadays, they have better performance than symbolic methods. There's less knowledge up front. So while symbolic models require experts to come in and provide knowledge into the system, you don't need as much of that knowledge up front in sub-symbolic models, right? All that information really comes from the data itself. They are easier to scale up, right? So building out a bigger architecture, providing more nodes in a network, you really just need more computing power, more memory, and if available, more data. And these methods, scaling them lets them take advantage of not just more data, but more data points, more variability in the data. So it's much easier to introduce noisy data and try to understand which parts are actually useful, which ones are contributing to a particular result. It's more useful for connecting to neuroscience. So this is quite important if we want to actually have computers talk to people, talk to humans, to understand their sort of signals. And so in that kind of work, it's much easier to have a sub-symbolic model that can handle the amount of information that's generated by these kinds of signals, but also to infer which signals are actually useful. And they're better for perceptual problems, so things that we can try to observe in the real world. So here's some kind of misnomers about these models. So can it learn? So sub-symbolic methods are known for being able to learn new information, but symbolic models are known for being static and not actually being able to incorporate new information once a model has been built. So this is actually not true. Symbolic models like inductive logic programming and case-based reasoning can actually use new information that becomes available and build out their model. And so as long as no contradictions are actually introduced, we can actually start putting in new new knowledge into the system and make new inferences later on. Is it non-monotonic? So can it actually unlearn new information? Right. So once the model learns something, can you actually teach it to unlearn it? Or can you provide contradictions that maybe will make the model inconsistent? So yes, actually you can. So the area of default logic allows you to replace default beliefs with new observations. And this actually allows a symbolic AI to unlearn information and learn new information in its place. So it's not as static as some people might describe it as. Now, what about the sub-symbolic models? Does it actually have symbols? Is everything just a vector? Is everything just numbers? Well, not quite. So when you go and train a classifier, you're actually giving it symbols. You're giving it things that labels for different kinds of images, right? So you tell it that this image is a cat versus a dog. So symbols are actually used in sub-symbolic models all the time. Right? They're sort of the key components that they try to learn, especially classifiers. Sub-symbolic models also learn relationships between two or more things. So for example, if you do an image recognition, let's say you want to recognize a face, one of the things that a model might learn is the orientation of eyes to a mouth, right? So these kinds of concepts are not explicitly defined, but they're implicitly learned by sub-symbolic models. So how does this all fit into the sort of the general AI world and all the work that's going on right now? So the way I like to look at it is how much is the work that we're doing contributing towards artificial general intelligence? And one thing I'll say is that I'm not saying that we will have artificial general intelligence at some point in the near future. I'm saying it's a possibility. I don't know when it will happen, but I like to think about it in terms of what would be needed. What kind of building blocks do we need to actually get us there? Right? So is AGI possible? Not yet. I don't think so. I think it will take some time. Another common question about it is it dangerous? And what I say to that is only if we let it act on the decisions or the outputs that it makes. Right? So having a human in the middle will prevent any kind of large AI system from really becoming dangerous. And what about sub-symbolic AI as AGI? One of the issues with sub-symbolic AI is that it doesn't have any explicit goals within the model itself. All you have is a set of outputs. Right? There's nothing inherent in the model that says these are certain goals that should be achieved. What you're really doing with sub-symbolic AI is here's some input, here's some output. Can you match? Can you learn to give me the output that I want given an input? Right? Generally, sub-symbolic AI cannot make their own goals. Right? These goals are really there to from the AI designer. Right? One example that I like to give here is if you try to build a system to solve cancer. Right? So if you give it a goal of get rid of cancer, one of the solutions it might come up with is to kill everyone who has cancer, and that will get rid of cancer. So that's clearly not the right solution, right? And so if we for the goals that we do give a sub-symbolic AI, we go back to that same question as above. As long as we don't let it act on the decisions or the outputs that it makes, I can't see an AI being dangerous to us. Another thing to mention here is that a sub-symbolic AI does pattern matching. Right? It connects different symbols to with different patterns, which allows it to actually connect different symbols or different concepts together through the data. But if the symbols and the goals are not there, if there's not something that we can actually understand and interpret, then it's really meaningless. The kind of information and the patterns that it identifies are meaningless to us, so we can't really use them. And what about the symbolic AI? So as I mentioned, goals are really provided by the AI designer, right? So as long as humans are providing the goals, I think we're safe. Right? However, that kind of reasoning must be constrained and well-defined. And so again, going back to the cancer example, if you tell an AI, whether it's symbolic or sub-symbolic, that you want a solution for solving cancer, you don't want it to come up with a solution like kill everyone who has cancer, right? And you most certainly wouldn't want to have it act on it. The nice thing about symbolic AI, though, is that you do define these rules explicitly right in the model, right? And so any problems that have goals and rules are not just solvable, but they're also explainable. And so once a symbolic AI gives you a solution, you can actually trace it back and understand how it came up with that solution. And that's really important when you do want to act on the outcomes. All right, so what about hybrid AI? So with symbolic rules to fill in missing data in sub-symbolic training, we actually have a chance, right? If we take the benefits of having large amounts of data in a sub-symbolic model, and if we take advantage of symbolic rules or symbolic models that incorporate subject matter experts' experience and knowledge, if we combine those two, then we actually do have a chance of building an AI that can be much more general than the narrow AI models that we're currently developing. And as I'll try to convince you, we already have hybrid AIs all around us. We just haven't really classified them as such. So what is the state of the field right now? So what I've done is I went to Google Scholar and I did a search on different terms that are related to this symbolic versus non-symbolic AI, right? So neural-symbolic is another term that people use. And I also looked at rule-based and neural network, but I excluded fuzzy rules because fuzzy rules are sort of in the middle. So I didn't want to conflate the work that fuzzy rule research has done. And I wanted to really focus on the symbolic versus sub-symbolic rules. And these are, on the left-hand side, are the number of publications over the years, starting in the year 2000. And you can see that in around 2016, we started seeing a really large increase in the number of publications. And so this is actually quite exciting because now everyone here knows that sub-symbolic research has been going on for at least 15 years with much success. But the symbolic AI has gone through a bit of a winter period. And so in 1980s, this work really started stagnating. The results were good, but it was very expensive to develop these kinds of models. And around 2000, people started using cheap GPUs, and so people revisited the work on neural networks, Jeffrey Hinton's work and others, and that really made it increase. Really saw an increase in the number of publications and researchers around the world that were developing new sub-symbolic models. And so it's really nice to see that there's an uptick right now, again, starting in 2016, with not just using symbolic AI models, which has been going on for since the 60s, but it's nice to see people actually combining these two models and taking advantage of the computational power that we have now and the knowledge sources that we get not from data, but from subject matter experts. There's a lot of conferences and sort of venues that you can publish in. I want to highlight Pascal Hitzler. He's a professor in the Kansas State University at the Computer Science Department. And he has been sort of working on this, this hybrid AI approach for quite some time. He's recently published a journal, Neural-Symbolic Artificial Intelligence, State of the Art. And this seems to be a journal that will be coming out yearly, because I know already some colleagues who are submitting their work to the next version of the book. So there's quite a bit of work going on. These are the venues that I found that were sort of most focused on these hybrid AI exclusively. But if you actually take a look and look for these kinds of terms, you'll see that this kind of work has been popping up across NeuralIPS and HCI and AAAI conferences and satellite workshops for many years. And so these are just the ones that are sort of focusing on that work, but this work has been going on for quite some time. Okay, so what actually is this neural-symbolic architecture? What does it mean for these two sort of approaches to work together? And so as it turns out that in '97, Maria Hilario published this report, kind of analyzing the different configurations that you could combine these two systems in. And when I started looking at these systems and what is currently being done, I could very easily put them into the right slot. So the observation I made is that the architecture proposals that Hilario made in '97 are still true today. Right? The only difference is that we've now created or come up with new subsymbolic models and new ways of integrating symbolic AI. So let me focus on the first one here. So unified strategies. So these are ones that use one method over another. And so neural symbolic processing, these are models that represent their entire domain and entire knowledge as just let's say a neural network, right? But in there somehow there are symbols or patterns that keep coming up that are sort of trained into the system, right? So one example is self-forming symbols, right? And you see this with self-organizing maps for edge detection, right? So I'm sure many of you know that you can program a edge detection filter into a neural network, into a CNN, right? But these things can actually be learned by themselves. So you don't have to pre-program a model with edge detection filters. These things can actually be learned by themselves. Another one is network capsules. So this is work that came out of Kashork and Jeffrey Hinton's work in 2019. And what these are sub networks that actually learn different components of an image. Right? So these are models that actually learn and break up different parts of a concept. In this case, you have a house with a tree, and you can actually learn different capsules, which are little sub-neural networks, to learn what these different shapes are and how they can actually work together as different parts of one structure, like a house. The next ones are connection and symbol processing. And these are broken down into localist, distributed, and combined. And so a localist connection and symbol processing is when each node is its own concept. And here's an example of a network that learns a linked list structure on the left, represented as a network on the right. Right. So this model, essentially each node is an individual concept that's defined a priori, and then the model learns the connections between them to recreate the structure on the left. Distributed are the neural networks that we're more familiar with, where you have a network or groups of nodes that represent certain concepts, and then if you combine them in a certain way with certain weights, they give you the concept that you're actually looking for to classify, like, for example, a dog and a cat. So this is sort of the standard neural network architecture that we've been using for years. And then combined is obviously a combination of the two. And if you think about some of the deep neural network architectures, those are really different configurations of subnetworks that perform specific tasks. So while let's say a BERT model doesn't learn particular concepts, different networks perform certain tasks to get you to solve a particular problem, like, for example, language translation or classification. The next one are hybrid strategies. So now we start getting more into actual models that do explicitly incorporate both a symbolic and subsymbolic representations. And these sort of fall into 4 different tasks that they can perform. So they can translate between neural and symbolic models and vice versa. They can perform refinements. They can perform embeddings. So if you think of like word2vec, for example, where you have certain words and relationships between them are embedded as a matrix with a set of weights. And one of my favorite use cases is explainability. So being able to translate a neural network into a symbol would fall under these translation hybrids. So one example of an explainable translational hybrid is LIME, or any of the models that try to explain why a neural network made a particular decision on an image. All right, so here you can see that it tries to infer from the actual structure of the neural network which parts of the image are being triggered when the correct result or the highest ranked result is coming up. And so this would be a translational hybrid. Another one is for making decisions when driving. And so looking at an image, identifying different components, this research makes a decision about what should be done. Should you go forward? Should you turn left, or should you turn right? And it actually, it doesn't just give you the explanation, but it also tells you why it came up with the explanation that it has. So for example, on the left-hand side, you see that it predicted that there's an obstacle, a person, and that the traffic light is red. And so it should stop. And that's what the downward arrow means under the picture. And then the explanation for this is the fact that there's a person, and you don't want to hit a person, so you should stop because there's a person. And if you sort of skim through these different examples here, you see that there's different scenarios for making different decisions, and an explanation of what are the key parts of the image that are leading to that decision. Another one, this is a really cool one. This is about common sense reasoning. Like I mentioned in the beginning, common sense reasoning is actually a very difficult task because it requires a lot of, and not just a lot of data that people learn over time, but it also requires a lot of intuition. And so this research is interesting in that it takes observations and text and uses a transformer to encode the different relationships of the words, and tries to understand sort of the semantic roles that each word or each phrase play in a particular sentence. And then it takes it a step further, and it actually tries to create new knowledge. Right? So it tries to identify things like, if, say, in this example, person X puts their arm around someone else, that person is caring. And so that's something that the program might learn from the data. Person towards person Y. Right? Errors are things that it actually creates from the data that it learned. And it can also generate new information about events that it hasn't actually seen in the past. Right? So for example, if it learns something about having fun, it can try to figure out different concepts that might go along with having fun, like going to the movies or buying lunch or throwing a party. Zhang and his colleagues have a really good paper about a survey paper about these different hybrid models that I would encourage you to check out. And they actually have a really nice categorization for these different systems. One of the things that they identify is the hidden semantics, so the hidden meaning behind the different connections. So this sort of goes towards explainability, but they also look to see which of these models are creating a set of rules to try to explain what the neural network is doing. And so you can see that these kinds of models interpret these neural networks and then translate them into symbolic AI representations. And they can do it at the local level. So for specific concepts, like we saw with Line, on semi-local, so looking at groups of concepts and networks, but also at a global level. So taking the entire model and try to understand how it functions internally. And so these are some of the results that they have. And again, I wanted to point out that the rule category here in this passive section is actually quite large. And what's really interesting is that at the global level, so for the full model, they can actually generate a set of rules for explaining why a certain outcome was produced by a model. Okay, and the final category under hybrid strategies is functional hybrids. And so functional hybrids are architectures that organize the either symbolic or subsymbolic function, right? So chain processing is something that once one let's say a symbolic model does something, it passes that to a subsymbolic model, right? And they sort of work together and passing information along a chain. Subprocessing is a similar approach, except it's hierarchical. So there are certain features that are done at a high level. Let's say some kind of organization. A task might be done to split, let's say, a data set or split different features into different groups, and then a sub-process or a child process starts doing work on them, and those can be broken down into different levels. Meta-processing. So this is processing that is done on the actual model building or training or testing, such as monitoring its performance, controlling what should be done, and monitoring performance in order to make improvements. And so you can see that a system might actually be improving by having a subsystem do the meta processing by improving the system more and more. And co-processing. So this is one where neural and symbolic AI are equal partners and they interact together, often working in parallel to solve a particular problem. And I'll show you that this one is actually one of the more successful ones, where they play equal roles. So in '97, when this research first came out, it was actually quite easy to put different systems into different buckets. Right? As you can see here, there is a lot of work that was going on in this hybrid AI space, but it was easy, and the systems were much simpler to identify where the symbolic ended and where the sub-symbolic started. But that isn't the case anymore. Right now, they're being combined in many different ways to solve a variety of new problems. So here's one for reasoning about images. So this work from MIT looks at an image, identifies the different components, and then tries to put it back together using spatial reasoning. Right. So understanding that a chair should not be on top of a desk, for example. It should know that a chair has legs, some kind of seat, and maybe a back, right? And it serves a certain function. right? So this is what I mean about reasoning about images. So once you have that kind of information, you can then start asking questions about an image. Like, for example, what is the color of the fire hydrant? Right? So identifying the different components and their properties will give you the correct answer, in this case being yellow. It can also do some arithmetic. For example, how many zebras are in the picture? So in this case, you would identify different zebras, and you would know that the question is that's being asked is about the quantity of those zebras. So you can, instead of just saying yes, there are zebras, or no, there are no zebras, you can actually say there are 3 zebras in total. So you can see that the sort of image recognition model that is a subsymbolic, in this case, a subsymbolic model, is combined with a reasoner or a symbolic reasoner to actually make decisions about what is being asked and what should be the answer. And in the second case with zebras, it actually knows to perform arithmetic to count the number of zebras. Another architecture, and this is actually a cognitive architecture. And cognitive architectures are systems that try to mimic the way that people think. So it's not just trying to recreate neurons that exist in our brains, but it's trying to recreate the different components of our brain and our way of thinking. Right? So in this case, we have a mind that may create different beliefs or hypotheses. We might have different observations that provide what we believe to be true. And this information is combined to generate a set of rules that tell us something about the world. And this new information is really the knowledge that we have about the world. Right? For example, knowing that on the image here you have a car and it has certain dimensions, certain probabilities of being different parts of the car, and so on. Another cognitive architecture that actually just came out this year is from LeCun. And what he's done, and I'll go into this example in a bit more, but what I wanted to highlight is that there is an explicit kind of modeling approach that's starting right now, where instead of having one giant model to do one thing, or maybe having a pipeline like a BERT model that performs certain subtasks that move data from one neural network to another, we're actually getting into these architectures that have different components handling different parts of a particular task, right? So for example, you have your perception to sort of identify what the world looks like and actually build a model of the world. You have this notion of self, or the actor. So an understanding of what the agent, what role it plays in that world. And there's this notion of a configurator. And this is sort of the controlling mechanism to decide which of these components should be triggered and when. Okay, so what I've been sort of presenting to you are different hybrid architectures, right? And so I wanted to highlight sort of what is the benefit of having these. I hope that I have convinced you at least a bit that these systems already exist. This notion of a neural symbolic, approach is not new. It's only now becoming more popular again, and people are starting to name it as such. And so, and some of the characteristics of these architectures, one is nonlinear problem-solving methods. Right? So this is, instead of having a pipe or one giant model doing one thing, these architectures use different methods to solve different problems, right? And those problems can be broken up into sub-problems and reasoned about separately from their representation, or from their perception, or from their data. The control for that sort of mechanism for these different problems and problem-solving methods, it could be centralized or decentralized. And I'll show you some examples of these in a couple slides. And the objective here is not to use a particular method or to focus on a particular method that one might know, but it's really to combine different methods and build the best tool for a particular job. So if a symbolic AI is good at reasoning, but is not good at identifying images, and if subsymbolic models are not very good at reasoning, but they're very good at identifying images, it really makes sense to combine these two methods so that you can identify parts of an image and then reason about them. And this is an example that you saw where the image reasoning research was trying to answer questions about images about zebras or fire hydrants or whatever. And finally, cognitive architectures. This is a very natural way of thinking. We like to look to nature to be inspired and about new techniques, about optimized sort of configurations of different methods. And so cognitive architectures are really ones that really try to replicate or at least be inspired by the way that we think. Right? They try to mimic specialized brain functions for maybe taking in input, processing it, representing it in some way, and then reasoning about it and coming up with outputs. And you may have heard of the System 1 and System 2 by Kahneman, thinking fast and slow. So this is a very popular kind of paradigm where System 1 is taking in information and making decisions quickly. So looking at short-term memory or having very sort of quick responses or reflexes about incoming information, where System 2 is more of sort of long-term memory processes, more reasoning that takes longer. And so often people like to break System 1 and System 2 paradigm into System 1 being a subsymbolic model, whereas System 2 it takes in more sort of knowledge, more explicit information that we may have in our long-term memory and reason through a particular problem and come up with the best solution. So next, what I want to show you is some examples of hybrid architectures that currently exist. And I'm going to sort of move to frame this part by showing you some work that was done back in the 80s and revisiting some work that I described already that is being done now on these hybrid systems. So one system that is very popular, used to be popular and is used now, but not explicitly, is the Blackboard architecture. And this is work that came out of Carnegie Mellon in the 70s. And the first sort of actual model that was built, it was in 1980s called Hearsay. And the way that the Blackboard architecture works is there are different knowledge sources that provide hypotheses about a solution. And these are not complete solutions to a particular problem because generally the problem is quite large. And so these are partial solutions to some problem that was posed. And each knowledge source performs a very specific task. And once it is asked to produce a hypothesis, it provides that information on what's called a blackboard. This is where the architecture's name comes from. And this blackboard is visible to all the other knowledge sources. So all information is not only visible by the different knowledge sources, but it's also interpretable by them. So this way, every knowledge source can talk to each other through this blackboard and understand the kinds of solutions or partial solutions that each of the other knowledge sources produces. The best way to sort of describe this is if you're brainstorming, or maybe if you're solving a puzzle with some friends, all of you are working together trying to solve little sub-problems of the puzzle. And everyone is contributing a little bit over time until you sort of find the final solution to the problem at hand. There's a loose hierarchy to the data that is on the blackboard. And what that means is that there's different parts to a problem and it's represented in different ways. And so there's no kind of linear way to contribute to a problem. You can start and end in any place that you see fit, depending on the kind of knowledge source that one is, and the data that's already available on the Blackboard. The focus of a Blackboard architecture is placed on parts of the problem that have the weakest solution or the weakest hypotheses. And so there's a controller that decides which knowledge source should function or should provide information to the Blackboard based on what information is missing, or maybe how good the current information is. So if one of the knowledge sources provides a hypothesis, but it's very low quality, maybe its confidence is very low, the controller might put focus on that and decide that a better solution needs to be provided. Okay? And then there's another set of knowledge sources that instead of producing new hypotheses, they actually augment or improve existing hypotheses on the Blackboard. Okay? And this work has been applied to different domains. The first application in 1980 that was fully built and complete was speech-to-text conversion, and I'll cover that in a second. Another one was image recognition and sonar signal analysis by Feigenbaum. So a bit about how these work. So I talked a little bit about Blackboard architecture and the different knowledge sources. And so now I wanted to spend a bit of time how the data is actually represented. And so here, here's a toy example of a set of knowledge sources in a Blackboard to identify koalas in an image. So rather than giving it some data to say, this is a koala, this is what it looks like, learn this pattern, like you would in a sub-symbolic model, in Blackboard, you actually provide a structure of what a koala would look like, right? So a koala has certain parts. It has a head, a torso, some limbs, different regions, and there's different lines that split those parts of a koala, and different knowledge sources that contribute different parts of this problem space, right? So one knowledge source might identify the lines that separate different parts of the image, right? So this is analogous to edge detection in neural networks. You might identify different regions, so different components of an image to identify different parts of the koala. Once you have these different parts, the controller knows to start looking for limbs. So once you have different components, you can start identifying which of these components might be a limb of the koala bear. And so you can see that the Blackboard architecture kind of has these data levels that have a hierarchy or have some kind of connection between them, but it doesn't mean that this is the way that the problem should be solved. The knowledge sources are independent and they can contribute to any level of a particular solution. So I wanted to discuss the hearsay project in a bit more detail. So this is the first Blackboard architecture that was actually implemented and running. It is the first speech-to-text conversion application that was developed in the 70s. And the way that it's structured is that a piece of data or sound is given as input, and each knowledge source breaks that up into different parts of speech. And when I say parts of speech, I don't mean different nouns or verbs. I mean different levels of interpretation of a particular sound wave or sound or an audio sample. Right? And this is the way that the hearsay 2 architecture looks like. So you can see that there's different knowledge sources, right? There's different segments of the sound that's coming in. There's different syllables that have been identified by some knowledge source. Those syllables are then combined into what sound like words. And so we start getting words being created from the syllables that were found. And we can start identifying word sequences, which then may result in creation of different types of phrases. And then that information is sent back to the interface to the user to say, this sound has been interpreted in to represent this particular phrase. And what's worth noting here is that the arrows that go between these levels, these are different paths that a controller might take when they call one knowledge source to contribute something. Right? So you can, for example, see that a syllable, let's say, was passed to a knowledge source which produced a word. Right? This would be the MOW knowledge source. And you can see that this is all sort of independent. It's very dynamic in the way that they work. There's no linear process. The data that's passed from one knowledge source to another can go between any level, right? So any information, the best information available is used to produce some new hypothesis that's placed on the blackboard here. Okay, the next hybrid architecture I wanted to mention is this one again that I'm revisiting. So this is from Jan LeCun, and it very much resembles a blackboard architecture in that it has sort of different components that are being learned about a particular input. And there's one controller, in this case it's called a configurator, that is determining which component should be active, which one should take available input and produce some output. The nice thing about this one is that it is actually a cognitive architecture, so it tries to mimic, excuse me, tries to mimic the way that people think, but also it builds this sort of mental model of the world, and tries to understand and interpret, and perceive the world around it, and then place the actor in the middle of that to understand how the actor should interact with that world. This is the way that it's described, it hasn't been implemented. This is a sort of a document that LeCun put out this year about what he thinks is going to be needed to create something like this. And so this is a purely subsymbolic model, meaning that it represents the states of the world as vectors. But there are explicit actions and state changes and explicit symbolic concepts that are built into the model. These are abstract concepts like events and transitions. And so this is what I would call a subsymbolic model that internally develops a set of symbolic representations within the world and actions of the actor. And the other thing that LeCun mentions explicitly is that this model will not make predictions. So it won't be able to make predictions about y given x. What it can do is create correlations, or identify correlations between x and y. Right? And this is important because it's not making predictions, let's say, about classifying something. All it's saying is that there's a relationship between two concepts, x and y, which is very similar to the symbolic representation, especially ones in ontologies that give you semantic relationships between two concepts without saying anything about either concept. Okay? So it's really all about identifying relationships between concepts and then inferring things about the world and how to make decisions about that world just based on understanding the relationship between two concepts. Finally, I wanted to mention AlphaGo. So AlphaGo, I'm sure you're all familiar with it. It came out in 2016 from from DeepMind, and they really kind of blew the competition away in terms of winning the number of games that they've won against other AI models that play Go and against human players. But I wanted to include them here because it's not a completely sub-symbolic model. And I'll show you why I think that is. So it's a very complex system. It has a lot of different components. The main sort of component that makes decisions is a reinforcement learning component that essentially learns what is the best move given a particular state of the world. Okay? And there's a couple of things that I wanted to highlight about this particular model and approaches like it. Excuse me. When I say approaches, I mean models that use reinforcement learning, but also use self-play to play against themselves to try to generate better and better games and learn better and better moves. So first thing, the AlphaGo model uses Monte Carlo tree search to generate new games. It's sometimes called Monte Carlo rollout. And it generates sort of plays into the future to try to understand what is the next best outcome given a particular situation. To be able to do this, to be able to mimic a game, to generate these sort of moves moving forward, you have to understand the rules of the game and you have to understand what the goal is. Without those two components, without knowing what the rules of the game are and what the goal is, you will never be able to generate these kinds of games. And the reason I point this out is because rules of a game and defining goals of a game, these are symbolic concepts. These are things that you explicitly define into the model as a set of rules, like quite literally as a set of rules about what is allowed, what isn't allowed. And you also provide an explicit definition of what the goal is. And here the goal is the end state that you want to reach. Right? So obviously winning the game. And in sub-symbolic AI, there really is no place for defining what a goal is or what the rules of a game or what the constraints of a game are. The only thing you do have, like in reinforcement learning, is providing a value function. Right? So you can provide a value function for one state over another, saying that this state is better than another. And that's okay, right? That's in reinforcement learning, that is sufficient. But if you actually want to generate a set of games and be able to perform self-play, you really have to be able to define what the rules of the game are and explicitly define what the goal is. And then the search algorithm can actually perform a search, a backwards search, starting from the goal backwards to the current state of the game. And that way you can actually see what the most optimal path is from your current state to the goal state. Right? So just to summarize, I wanted to highlight the fact that models like AlphaGo, they use self-play in combination with reinforcement learning and Monte Carlo tree search do actually have a symbolic component to them. Okay, so the last thing I wanted to cover is a project that we're working on at the University of Toronto at the Center for Social Services and Engineering. And this is work that we are doing with my colleagues, Daniela Rosso, Mark Fox, and Disho Liu, and with our data partners, HelpSeeker Technologies. This is part of a project from the Supercluster Fund. And we are trying to develop a model of social services that encompasses all the information about the different services in Canada. And I'll get into that in a bit more detail. But the model that we're creating is SMILE, it's semantic role extraction. And the key goals of this project are to take text like this you see here. It's a description of a social service that describes what they do and who they do it for, and to be able to identify different parts of this text, right? To understand what the services are, what kind of resources they use, and who the clients are of that service. And so we want to be able to understand who the service is, what they're doing, and who they're helping. And the second goal is to identify sequences of these kinds of satisfiers, or these different services, and understand how to move from one component, from one service to another, and how a client can actually move between these services to meet their goals, meet their objectives. Okay, so what's the motivation for this work? So currently, or at least in 2021, there were 65,000 social service providers and over 170,000 agencies that work within that space, either providing services or providing assistance to those 65,000 services. In Canada, in 2021, there was 4.9 million Canadians that live in poverty. There's 400,000 new immigrants coming into Canada every year, and there are 44,000 refugees that are immigrating to Canada. And I think that number is now growing. At the same time, there are organizations that are called social purpose organizations, or SPOs, that actually deliver very specialized services to through a variety of programs to these different clients. And they use what's called an impact model to understand whether they are actually contributing to their clients' lives. So whether the services that they're providing are actually helping people achieve their goals. Now, at the same time, the Canadian federal government coordinates this private and public agencies to fund these social purpose organizations, and tries to analyze whether the funding that they provide actually gets to the clients that they were meant to help. Now, this is actually a very difficult task to understand whether the funding that's provided actually gets to the clients, whether the funding you provide actually pays for the services that are most beneficial to clients. There's a couple of challenges here. One is it's actually a very difficult process of navigating these different SPOs and understanding which programs or which services you're eligible for and which ones you should use, and understanding the efficacy of the services that's assigned to a particular client is difficult. Okay? So understanding how well a service is doing in helping their clients is a very difficult task. So one thing that has been developed over time is the Common Impact Data Standard. Oops, sorry, I don't know why this is playing. All right, let me just play it this way because I don't want it to go by itself. So the Common Impact, the Impact Management Project is a project that tries to identify how to measure impact in this domain. And it has been developed by over 2,000 organizations working together to understand what the outcome is that should be happening, who it's going to, how much of it is actually occurring that's helping the person or the who, how much is actually contributing to the outcomes that the who is looking for, and what the risks are. And at the Center for Social Service Engineering, we've developed a Common Impact Data Standard, which is an ontology that tries to identify how those services are provided by identifying the inputs, the activities that are performed in social services, what the outputs are, and ultimately what the outcomes are that a client is looking for. And I won't go into too much detail here, but the ontology itself is a symbolic representation of the social service domain, and it identifies the impact, or it's a data model that helps you identify the impact of those service provisions to a particular client group. All right, let's see if I can run this properly. Okay. So to give you an example of what an ontology is, or specifically what the Common Impact Data Standard is, it's a representation of the social service space. It identifies different concepts and the relationships between them. And so here we start with an organization, which is a particular logic model. That logic model focuses on a particular stakeholder and has a set of programs. That stakeholder is really a client, in this case, with a set of characteristics. Let's say that they're an adult and a student, and they have a particular outcome that they're interested in, like finding a job, and a more of a long-term goal in getting education, right? So one way of finding a job is to enroll yourself in further education. Next, each program has a particular set of services, and those services have a subset of activities with inputs and outputs. Those outputs have a set of indicators that you can measure how well the output is how much output is actually being produced by an activity. And through that, you can actually generate an impact report to understand how much that output is contributing to the overall outcome that the stakeholder is actually interested in. Next, we have a set of events. And so events are really activities that transition a person from one state to another. And here we create events and link them to the previous event and the next event that's occurring. And this allows us to have a symbolic representation of the state of the world, but also how one state changes to another through these events. So here's an example of how an event might be used. We have a client who's a stakeholder who is currently middle school educated. And one thing that might happen is there's an education event that happens to this person. And so once that event occurs, the client state changes from being middle school educated to being high school educated. And the ontology allows us to represent these different relationships that actually transitions a particular client from one state, let's say the middle school educated state, to another state, in this case being high school educated. So these are sort of symbolic ontological representations of these different concepts that are required to represent a client's state and how they transition from one state to another, and also how different services can change these states. So let's say a school might help a client move complete what a plan that we could generate actually looks like. So if we begin with someone who is a new immigrant and wants to be financially independent, that person may need a higher level of language skills. So let's say it might not be enough to just speak English, but you actually have to have a professional vocabulary to get a better job. And so this kind of plan might take a client with a particular characteristic, being a new immigrant that has a goal of financial independence, and move them through the system. So we're actually guiding them through the education system, understanding how to evaluate them, what the next step in the process is, and then guiding them through the different options that they might have, right? So in this case, depending on the language skills that a person has, they would take a different path. But this would allow us to transition a client, or understand how to transition a client from their current state, meaning wanting financial independence, to actually reaching their outcome of having a better job. Okay? So that's sort of the main goal. And these ontological concepts here are really symbols for these different concepts, and we define the relationships between them. So we want to build up this kind of plan using these different ontological concepts. So towards this purpose, we've developed SMILE, the semantic role extraction, and this is a Blackboard architecture, which I'll explain in a second, and it's based on the ontology that I just defined, and it focuses on the need satisfiers and planning components and the factors related to specific clients and services. Right? So we take the ontology that I just described, which is the Common Impact Data Standard, and its extension, the Compass ontology, in the different events, client services, and needs that it represents. We create a taxonomy of different terms so that we're able to actually represent not just different services, but also different characteristics of the clients. And we built out this unified vocabulary of these terms, and so that we can have different service providers represent their own, let's say, their goals or their services in whatever way they want, and map them to our own representations. And this allows us to connect different representations of these services by different service providers into a single meaning. And so that when one person says that they provide housing, they mean the exact same thing as someone else that might say that they provide homes or they provide shelter. But what they're really talking about is the same thing, meaning they want to provide shelter for somebody. So through this sort of unified vocabulary, through these taxonomies, through these different concepts, we're able to represent these different symbolic representations of these concepts, the relationships, and unify different interpretations of these concepts into one definition that the program can actually use to generate different plans for a client. Okay, so the question then is, so if you have all this information, you have all these concepts, you have the service descriptions, how do you actually extract this information? How do I identify what is a program, what is a service, and what is a client? And how do you link those concepts together and build these sort of semantic relationships between these concepts that you have in the data? So I'll show you sort of our attempts at this, and I'll show you how what the current solution is. And so the concepts we're looking to find are the program names, so to understand what the programs actually are, what the need satisfiers are, and these are resources that are actually used to deliver the services, right? So it's not enough to say that you are, you provide housing for people. We actually want to know what it is that you're actually providing. Are you providing the actual homes? Are you providing help with furnishings? Are you do you help somebody with a referral to a housing program? So what is the actual resource, the need satisfier that you're providing? We also want to identify different client characteristics. So we want to identify when a client is being described, what their needs are, what their desired state is. We want to find service and client descriptions that are more general than, let's say, a client characteristic. So it's not specifically identifying characteristics of the client or the service, but it's more of like a general description that may help us later on to understand what the service of the client is. Same for need satisfiers. And finally, we want to know what the requirement criteria is. And once we have all these different components, we can actually generate a set of plans by connecting different services together and to generate a plan for a particular client based on their characteristics and their needs. So a couple things that we tried. Our first attempt was to perform named entity recognition using sort of off-the-shelf models. These are sort of the best performing models currently in the literature. And one thing we found was that this is the F1 score for each of these, and you can see that they're actually quite low. So the published results for NER tasks were in the high 80s, high 90s, on a test corpus. But when we actually apply these models to our data and to our entities, you can we're underperforming in
But can you hear me?
Yes.
We lost you for a few seconds. Can you go back to the previous slide and yeah, this one, please.
Sure.
Can you, if you don't mind explaining it again?
Sure, absolutely. Yep. Sorry about that. So the first task we wanted to perform is a named entity task to identify the different concepts in our text. And we wanted to see how well existing NER models, sort of the best of the best, perform on our data. Right? So these are models that are normally trained on identifying person names, locations, events, and things like this. And so we wanted to see how well those tasks are done on our corpus. Right? So in our corpus, in this case, are descriptions of different services. And so if you remember,
But seems like, sorry, but seems like we lost you again. And now you are back. You're back.
I'm back. Okay. Sorry about that. Yes. So what the task is, the named entity task is to take a service description and identify the different components, what the service is, what resources they're providing, and who they're providing to. And so these are the concepts that we want to extract from the text. And these are the F1 scores for off-the-shelf models that perform the NER task. And these models have an F1 score of high 80s, high 90s on the test corpus that most of these are trained on. But as you can see that on our corpus, they actually performed quite poorly. And so what this tells us that there are no existing NER models that were trained on something similar to the data that we have, which is the service descriptions, and that the concepts that we are actually interested in are not easily inferred or mapped to the concepts that these models are trained to recognize. So essentially, we could not use these models as they are. So the next thing we tried is a rule-based named entity recognition architecture. And the way that this works, and I won't go into too much detail here, but this work has already been published, so you can look it up. But essentially, what we did, we used an off-the-shelf NLP parser to perform parts of speech tagging, dependency, and co-reference resolution, and then we applied a set of rules to break these parsed entities into what we call T triples. And so these T triples are really terms that were connected together in some way. So an example of a T triple might be a program offers a service. So that's a triple. Service for a client, right? Where service and client are the actual instances of the services. So you can say housing for homeless youth. You can say St. Mary's Church provides a soup kitchen. Right? So these are the kinds of triples that we generated. From that, we resolved the co-references. We created a chained rules to actually connect different triples together, so we can have kind of more complex statements like St. Mary's Church offers housing for homeless youth, right? So we can chain these different concepts up through their relationships to identify what is being offered and to whom. And then that information then was used to generate these semantic roles to actually understand who is providing what to whom, when, why, and so on. And so this actually worked quite well. It worked well for certain concepts and not very well for others. So here I've highlighted the entities that we feel performed better than others. So we were able to identify client characteristics, client descriptions, need satisfier descriptions, and program names. We weren't very good at identifying the needs, the desired states, requirement criteria, and descriptions of the service. So so while this is better than the off-the-shelf NER models that I showed you before, this still is not broad enough to use in sort of towards our main objective, which is generating a set of plans that connects different services to clients. And so we decided to create a more dynamic architecture to perform different parts of this task. And so this is why we use the Blackboard architecture. And so Smile is an architecture and a hybrid AI architecture for identifying not just the different terms in these sort of difficult to parse service descriptions, but actually connect these terms together so that we can identify these different ontological concepts like services, clients, the fact that service is provided to a particular client, and so on. And so if you recall, the Blackboard architecture has this Blackboard where all the information is stored, different knowledge sources that supply all these different pieces of information called hypotheses, and a controller that sort of decides which hypotheses should be generated next. And so within Smile, we have a specific hierarchical data structure that tells the system how to parse particular text. And so here we begin with some text. We split it up into words. Those words can be broken down into phrases and parts of speech. We then have co-references, dependency trees. We then break them up into these triples that I was talking about, which identify different words and their semantic relationships. And from that, we can actually generate a set of named entity recognition instances, and finally resulting in the relationships between those entities. Now, these concepts, SPO and above, these are all sort of either standard NLP processing outcomes, and the SPO is what I showed you in the previous set of slides, where we actually generate a set of triples and generate semantic roles. And so the main contribution, or the main new addition here that we're putting into Smile, is the NER component. And the NER component is based on the ontology itself. And so here we actually supply information about what we're looking for, these different symbols that we're looking for, right? So we want to identify a service. If we identify a service, we might start looking for a program, because we know that a service is provided by a program. We know that if we find a particular, excuse me, stakeholder, then we might want to start looking for the logic model or the program that stakeholder is connected to. So we use the ontology to let us know how these different concepts are connected, and how to actually how to connect the different knowledge sources to find these different components. So I won't go into details of each of these, but I do wanted to sort of highlight what kinds of knowledge sources we have. So we have the parser, the tokenizer, to actually process a piece of text. We have our rule-based parsing. We have call reference resolution, both for a particular word and also for the triples that we're generating. We have a dependency knowledge source that not only generates hypotheses about dependencies between words, but also makes corrections, because often these dependency trees are incorrect. We are using off-the-shelf NER models that I mentioned before for some edge cases. We are using a rule-based NER that I presented to you a couple slides back. And we've also developed a question and answer library for generating questions or queries in the text to identify NER components to generate new phrases. We also have a rule-based phrase extraction knowledge source. And finally, we have a set of knowledge sources that expand the relationships between terms, right? So creating a chain of named entities through their semantic relationships that we found in the data. And so at the end, what we have is this a structure for the different data levels that we're looking for parsing text. We also have different data levels based on the ontological concepts. And we also have this controller that can ask ask different knowledge sources to generate different hypotheses based on the information that's available currently on the blackboard. And that is the end of the presentation. And thank you for your time. I'm happy to take any questions.
Thank you so much, Bart. Turn on my camera and yeah, thank you so much. I really like this Smile project. Thanks for sharing that information. Just a quick question. With all those new information that you added to your Smile project, whether the accuracies and sensitivity improved with the latest one, or you're still having the same issues?
Yeah, the accuracy of the NER task has improved, especially with the question and answer module, because we're able to generate our own questions and ask very specific questions. The nice thing about this model is that we can use a pre-trained off-the-shelf Q&A model without having to train it on our own data, like we had to with the NER models.
Another quick question before we move on to a student question. Can you share the GitHub repository and the paper on this project with Andrew?
Sure,
and
absolutely.
We can share it with students as well. Thank you so much. Maybe Andrew, you can select 5 questions.
Yeah, a bunch of students kind of messaged me throughout, and I'll just remind students to please submit that Google form as soon as possible, because we will close it once class ends. Yeah, the first one I'll pick. If we were to build a system incorporating the purpose of artificial general intelligence, then should we use a symbolic approach or non-symbolic approach? Why?
So I hope that I have convinced you that you should be using hybrid systems. Why? So if you just use symbolic, you really need a subject matter expert to code those rules, code that information into the knowledge base, right? So you need someone to really explain how things work in the world, which you can imagine is an impossible task, because there's no one that knows everything, and some concepts are just really hard to capture as symbols, right? They're much easier represented as just data that is occurring, like patterns. It's hard to describe a pattern, But if you put it into, if you give a data set that exhibits that pattern, then it's much easier to represent that in the model. And the flip side of that is you should be using sub-symbolic models as well, because you should use symbolic models if the data is not there. So it's really hard to collect data for a particular context. It's much easier to represent that as concepts. I'll give you one example. IBM Watson for health. One of the reasons that project failed was that the recommendations that were being provided to doctors were not context specific. And so one of the doctors kind of pointed out that the solutions that you're giving me are great, but I can't use them because here, like let's say in North America, the solution for cardiac arrest is very different than in China, right? Completely different context, completely different resources, completely different medical histories, right? So having additional data is important, and so having a hybrid system, I think, is a much better way moving forward.
Thank you. The next one I'll pick. As said in the presentation, subsymbolic AI is not able to define its own goals, but it is also true that it is capable of decision-making and common sense reasoning. So I would like to ask if the decision-making is dynamic, because it might be able to feed the inputs on its own as it learns. And if yes, how will it work in real time?
So subsymbolic models cannot perform common sense reasoning. The one exception to this right now, at least, is Comet. It's that transformer model that I showed you. And what that actually does is, the reason they say it's common sense reasoning is for this reason. I'm sure that you've seen a lot of NLP generation models that generate text produce very weird results, right? So if you ask a question like, why do my socks like to do yoga? They will try to kind of give you some kind of answer that combines words that they found that were somehow related to the ones in your query, and try to use some kind of grammatical rules to generate proper grammatical sentences. But those sentences might not make any sense, right? So if you type in a question like, why do my socks like to do yoga? They might tell you something about yoga and why some people like to do it, and say, and that's why your socks like to do it. But common sense will tell you that that's not actually true, right? So, and not only is it not true, it doesn't make any sense. The question doesn't make any sense. And so, common sense reasoning that you can represent in a symbolic AI will say that socks don't do yoga, right? You might wear socks while you do yoga, but socks don't do yoga. They have no agency, right? They have no need to do yoga. What the Comet project tries to do is, and it actually was much more successful in these weird questions, because it specifically tried to find relationships, not just sort of, which words go together, but actually focused on identifying the relationships that exist between words. And so that's where the common sense part came in. It knew that certain words were connected by let's say, a verb, to tell you that, one concept performed another concept. Right?
Okay, thanks. The next one. Since cognitive architecture can replicate the decision-making process, can they also be used to replicate memories? If so, can these memories have bias, like people often remember things differently based on their own bias?
Yes, absolutely. You see this all the time. A cognitive architecture is, especially one that incorporates subsymbolic models, it's only as good as its data, right? The nice thing about symbolic models is that you can put constraints on what kind of inferences you can make, or what kind of classifications you can make. And so so in a black box model, it's hard to remove someone's ethnicity unless you retrain it or unless you perform some kind of masking to change the model, right? Some kind of knowledge transfer without the race attribute. But to an existing model, it's hard to remove it. And so in a cognitive architecture, you would need some kind of a component to worry about these kinds of things. And those will be contextualized, right? Like race would be something that you might want to consider, put in a set of rules to only consider race in certain instances. So if you're going to be building a cognitive architecture and you want to model it as a brain, the question is good because you would be putting it somewhere in the memory module, right? It would be in the retrieval process of your memory. That's where the bias correction would exist, right? So you might have a very biased memory in your memory bank, but when you actually go and retrieve it and reason about it, you can then remove it using some kind of symbolic reasoning.
Okay, thank you. The fourth one I'll select here. Can SMILE process be reduced to a complex flowchart with conditions and use regex for recognizing the different vocabulary used from the service providers?
No. And I don't have a good answer for why, but I can tell you that we tried it. We tried to have actually the rule-based named entity recognition that I presented. That's the one that had that sort of flowchart that went around. That one tried to not use regex, but tried to use different combinations and patterns of parts of speech to identify different components. So for example, you would know if you knew that you had a noun, a verb that is a synonym of provides, and another noun, possibly plural, then that is probably a program that provides a service, right? So you can have rules like this. And so not regex, but parts of speech. So a state machine based on parts of speech. But as I showed you in the slide, in the results section, we were only able to cover certain entities. So that kind of pattern only works for certain entities and not for others.
Okay. And then the last one, as a combination of neural networks in different ways can learn higher dimensional vector from data, can the symbolic AI learn such higher dimensions or at least be able to represent such vectors?
So vectors are by definition incompatible with symbolic AI. The only caveat to that is that you can have an encoding that translates from one to the other. Right, so word to vec is a great example because you have specific words that represent certain things, and while you can learn sort of the frequency distribution of different terms, right? So see which ones occur together, you don't really get any understanding or any semantics out of that, right? So what you could do is to take an embedding that you've learned between, let's say, between for some corpus, and then map it to a symbolic representation of those terms, right? So WordNet is a great example. If you take a WordNet, which is a sort of a very, very sophisticated thesaurus, essentially, with a nice hierarchy relationship for different words, combine it with a word-to-vec embedding, you can start reasoning about different words to generate different meaningful sentences, right? So I'm sure you've all heard the example for word-to-vec where if you take king and you remove male, you get queen, right? That's a very powerful semantic relationship, but it doesn't mean anything unless you have an ontology or a symbolic representation to tell you how kings and queens are represented or how they're related to each other. Just to kind of give you a more complex example. So in this one, king and queen, you have this notion of gender, but you don't know what gender means. In a symbolic representation, you can have a very explicit definition of what, not just what gender means, but you can actually have a family tree. So you can reason about things like, if I have a king and a queen who are married and they have kids, I know who maybe the next in line might be. And let's say if there's a rule for being only males can be kings, you can start reasoning about who the next in line is for the throne, right? So you can basically go down the family tree hierarchy to find the next sibling of the parents, their next children, and once you find someone who is male, or once you find a nephew, let's say, of the king, you know that they're related to the king and they're male, and so they're eligible. So you can start reasoning about these kinds of things that are represented in the symbolic AI, but those kinds of things are very difficult to represent in a sub-symbolic model.
Perfect. Thank you very much.
Thank you, Bart. I know we have huge list of questions, but I think we'll not take any more question, and it's almost 1:45. So thank you once again, Bart, for joining this session and presenting your very innovative research and ideas on artificial intelligence and kind of its future and application too. Thank you.
Thank you very much. Thank you for your time. Thank you for organizing this, Andrew. It was great to come back to Lakehead. And thank you for the questions.